Lab 3, Black Hole Orbit, presented by Andrea Otero. For lab number 3, the purpose was different than lab 1 and lab 2, because instead of predicting the motion of an object, we had to figure out the mass of a black hole. In order to do so, the position of a star and its mass was provided, as well as the constant position of a black hole for a large period of time, and based on such positions, we were able to construct a model that was able to calculate the net force acting on the star based on the momentum principle. Using the net force acting on the star, we were finally able to calculate the mass of the black hole using the universal law of gravitation. The Python code was constructed in order to be able to calculate the net force acting on the star. As a fundamental principle, we use Newton's second law, but based on the momentum principle of the star. The code used the given positions of a star over a large period of time, with a delta t of 1 Earth day, which is equal to 86,400 seconds, extracted from a CSV file. Based on such data, the model was able to calculate the velocity of the star from one position to another over each time interval. Since we had the mass of the star, the momentum of the star for each period of time was also calculated, and using the same time interval, we were also able to calculate the rate change in momentum in 1 Earth day. Finally, the Python code calculated the net force acting on the star by using the momentum principle, which established an equivalency between the rate change in momentum and the net force, saying that the change in momentum over change in time is equal to the net force. We were then able to finally find the perpendicular and parallel component of such force by using the parallel and perpendicular components of the momentum. Running the Python model, we are able to see the motion of the star orbiting the black hole, with the yellow arrow representing the net force, a blue arrow representing the perpendicular component of the force, and the black arrow representing the parallel component of such force. Using the law of universal gravitation, we were finally able to calculate the mass of the black hole, because we had the mass of the star, the distance between the star and the black hole, since we had the positions of both, and the net force acting on the star, calculated by the computational Python model constructed. Since the mass of the black hole was the only unknown, we were then able to use the equation in order to calculate the mass of the black hole. As shown in the presentation, we can see the calculations. Finally figuring out that the mass of the black hole in this case was of 2.95625 . The first discussion question established how are the force net perpendicular, the force net parallel, and the force net different from the change in momentum over change in time perpendicular, the change in momentum over change in time parallel, and the change in momentum over change in time. Well, using as a fundamental principle Newton's second law and developing it, dp dt, or the rate of change in momentum, is equivalent to the net force. However, they are different physical concepts that end up being equivalent to one to another when applying Newton's second law, meaning they are not the same concept. While force is an interaction between two particles, momentum, on the other hand, is a fundamental property of a system. Additionally, if we want to change the momentum of an object over a period of time, we have to exert some force over some period of time, showing their relationship rather than their equality. The second discussion question stated, imagine the black hole whose mass you found was removed and a different black hole was placed in the same location. Assume the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole. Could you tell the difference? Well, if the motion of the observed star remains the same, meaning unchanged, it is impossible to have a different mass for the black hole, since only when the mass of the black hole changes, or the distance between them, will the motion of the star change. Since in this case the motion of the star is not changing, it would not be possible for the mass of the black hole to change, since as we saw while constructing the model, the position of the star determined the net force acting on the star, which then determined the mass of the black hole. Therefore, if the mass of a black hole changes, the net force will change, and if the net force changes, due to Newton's second law, it is evident that the velocity of the star will change as well, which will consequently affect the star's motion. Thank you for your time.